Okay, we're live, and so today we're going to walk through advanced Solidity Concepts. Here are the chapters, and you can see we learn about ownable contracts, gas. That seems to be a very important topic. Storage. You know, I got some coffee here today. Just brewed it. I got some water. It's let's get started. Chapter 1: Immutability of Contracts. Up until now, Solidity has looked quite similar to other languages like JavaScript, but there are a number of ways that Ethereum dApps are actually quite different from normal applications. To start with, after you deploy a contract to Ethereum, it's immutable, which means that it can never be modified or updated again. The initial code you deploy to a contract is there to stay permanently on the blockchain. This is one reason security is such a huge concern in Solidity. If there's a flaw in your contract code, there's no way for you to patch it later. You'd have to tell your users to start using a different smart contract address that has the fix. But this is also a feature of smart contracts. The code is law. If you read the code of a smart contract and verify it, you can be sure that every time you call a function, it's going to do exactly what the code says it will do. No one can later change that function and give you unexpected results. Is that a little flash on the stream or something? Anyway, let's take a little sip. External dependencies. In lesson 2, we hard-coded the CryptoKitties contract address into our dApp. Did they call these dApps? I wonder. But what would happen if the CryptoKitties contract had a bug and someone destroyed all the kitties? Good point. It's unlikely, but if this did happen, it would render our dApp completely useless. Our dApp would point to a hard-coded address that no longer returns any kitties. Our zombies would be unable to feed on kitties, and we'd be unable to modify our contract to fix it. For this reason, it often makes sense to have functions that will allow you to update key portions of the dApp. For example, instead of hard-coding the CryptoKitties contract address into our dApp, we should probably have a set kitty contract address function that lets us change this address in the future in case something happens to the CryptoKitties contract. Put it to the test. Let's update our code from lesson 2 to be able to change the, sorry, got distracted. Let's update our code from lesson 2 to be able to change the CryptoKitties contract address. We'll delete our line of code where it's hard-coded. We'll change the line where we created the kitty contract to just declare a variable. Don't set it equal to anything. Create a function called setKittyContract. It will take one argument, an address, and it should be an external function. Inside the function, add one line of code that sets kitty contract equal to kitty interface address. If you see a security hole with this function, don't worry, we'll fix it in the next chapter. Okay. So they're saying delete the line of code where it's hard-coded. Change this to just a declaration. You got it. And then set kitty contract address method here. Create a function. Yep. Function set kitty contract address. And it will take an an address called address. And it should be an external function. So I believe you put external here and you open up the braces. Cool. Let's check our answer. Wrong and wrong. What do we do wrong? I think we have the blank spaces that it doesn't like. What did I do wrong here? Oh, I forgot to do step 4. Add one line of code that sets kitty contract equal to address. Or not. Equal to kitty interface of address. Okay. I sure can read well, right? Kitty interface of address. So we're just moving what we had as a definition here into a function. Okay. Woohoo, you've triumphed. All right. Chapter 2, Ownable Contracts. Did you spot the security hole in the previous chapter? Set kitty contract address is external, so anyone can call it. That means anyone who called the function could change the address of the CryptoKitties contract and break our app for all its users. We do want the ability to update this address in our contract, but we don't want everyone to be able to update it. To handle cases like this, one common practice that has emerged is to make excuse me, to make contracts ownable, meaning they have an owner, you, who has special privileges. Okay. Below is the ownable contract. Open Zeppelin's ownable contract. Below is the ownable contract from the Open Zeppelin Solidity library. Open Zeppelin is a library of secure and community-vetted smart contracts that you can use in your own dApps. After this lesson, we highly recommend you check out their site to further your learning. Give the contract below a read through. You're going to see a few things we haven't learned yet, but don't worry, we'll talk about them afterward. It has an owner address and provides basic authorization control functions. This simplifies the implementation of user permissions. I love to see it. That is one of the biggest problems in so many languages. Their user permission thing is just a bolt-on. Maybe this is bolt-on, we'll see. Okay. So we have an address that's private called owner in this ownable contract. Okay. And it has an event, ownership transferred. Ah, interesting. The ownable constructor sets the original owner of the contract to the sender account. Message sender. Okay, so when I make an ownable transferred from wherever this was created, I guess, to the owner. Return the address of the owner. Okay. Throws if called by any account other than the owner. Only owner function. You run the require. Okay. Return true if message.sender is the owner of the contract. Function is owner. Public view returns bool is message sender equal to underscore owner. Allow the current owner to relinquish control of the contract. Notice renouncing to ownership will leave the contract without an owner. It will not be possible to call the functions with the only owner modifier anymore. Renounce ownership, public, emit ownership transferred from the owner to address of 0. And right up here, our address. There we go. Yeah, the owner is set to address 0. All right, next function. Function allows the current owner to transfer control of the contract to a new owner. The new owner, the address is to transfer ownership to. Function, transfer ownership, address, new owner, public, only owner. Transfer ownership to new owner. Transfers control of the contract to a new owner. Parameter. Wait. Allows the current owner to transfer the control of the contract to a new owner. The parameter, blah. Okay. Transfers the control of the contract. Okay. So it's essentially just require, like we had. It's not the original. And emit, ownership transferred. And set our owner to the new owner. And our emit event is up here, ownership transferred. Cool. A few things here we haven't seen before. Constructors. Constructor is a constructor, sentence, which is an optional special function that has the same name as the contract. It will get executed only one time when the contract is first created. Yes, that is what a constructor is. Function modifiers. Modifier, only owner. Modifier are kind of half functions that are used to modify other functions, usually to check some requirement prior to execution. In this case, only owner can be used to limit access, so only the owner of the contract can run this function. We'll talk more about function modifiers in the next chapter. And what that weird underscore semicolon does. Did I miss that? I think I kind of like thought about it, but didn't really say it out loud. Where is it? Emit, public, modifier. Interesting. Yeah. Okay. So I guess it we'll stay within the bounds of how Solidity talks. Because I think these are like first class functions where you can pass a function to a function. And that's kind of what's going on here, but we'll see what this tutorial says for sure. Function modifiers have functions, limit access, indexed as a keyword. Don't worry about this one. We don't need it yet. So the ownable contract basically does the following. When a contract is created, its constructor sets the owner to the message sender, the person who deployed it. It adds an only owner modifier, which can restrict access to certain functions to only the owner. It allows you to transfer the contract to a new owner. Only owner is such a common requirement for contracts that most Solidity dApps start with a copy-paste of this ownable contract, and then their first contract inherits from it. Wow. All right. Since we want to limit set kitty contract address to only owner, we're going to do the same for our contract. Put it to the test. We've gone ahead and copied the code of the ownable contract into a new file, ownable.sol. Sick. Okay. Modify the zombie contract to inherit from to inherit is ownable. Well, I have to import it, right? Uppercase, lowercase. I think I have to do this. Ownable. Yeah, that's what they're saying. Okay. Check answer. Oh, got my semicolon. Okay. This is like, so far my review of it is like, this is kind of like an in-between of C and C++ in terms of like the types it has. You need the semicolons. But I like it. There's no but actually. I can't wait to see how it links up with JavaScript. Anyway, now that our base contract zombie factory inherits from ownable, we can use the only owner function modifier in zombie feeding as well. This is because of how contract inheritance works. Remember, zombie feeding is a zombie factory, and zombie factory is an ownable. Thus, zombie feeding is also ownable and can access the functions, events, modifiers from the ownable contract. This applies to any contracts that inherit from zombie feeding as in the future as well. Function modifiers. A function modifier looks like a function but uses the keyword modifier instead of the keyword function. And it can't be called directly like a function can. Instead, we attach the modifier's name at the end of a function definition to change that function's behavior. Wow. Let's take a closer look by examining only owner. Let's see. Right. Okay, so we're just restating the code we saw before. Notice the only modifier on the renounce ownership function. When you call renounce, all right, let's look at renounce ownership. It's a public only owner. When you call renounce ownership, the code inside only owner executes first. Then when it hits the underscore semicolon statement in the only owner, it goes back and executes the code inside renounce ownership. Okay. So while there are other ways you can use modifiers, one of the most common use cases is to add a quick require check before a function executes. Interesting. In the case of only owner, adding this modifier to a function makes it so the only owner of the contract, you, if you deployed it, can call that function. In the case of only owner, adding this modifier to a function makes it so only the owner of the contract, you, if you deployed it, can call that function. Okay. Note, giving the owner special powers over the contract like this is often necessary, but it could also be used maliciously. For example, the owner could add a backdoor function that would allow him to transfer anyone's zombies to himself. So it's important to remember that just because a dApp is on Ethereum does not automatically mean it's decentralized. You have to actually read the full source code to make sure it's free of special controls by the owner that you need to potentially worry about. There's a careful balance as a developer between maintaining control over a dApp such that you can fix potential bugs and building an ownerless platform that your users can trust to secure their data. Put it to the test. We can restrict access to setKitty's contract address so that no one but us can modify it in the future. We can now restrict access to setKitty contract address so that no one but us can modify it in the future. Add the only owner modifier to setKitty contract address. Okay, let's go there. setKitty contract address, external. What's going on here? Only owner. Sick. Okay, here we go. I just realized I have all my tabs open in this stream. Just for aesthetic purposes, I'd like to change that. So bear with me one moment. Let's get this separated out. Full screen. Oh, I see what's going on here. Okay. Let's change our thing, and it's going to be, crypto zombies. Okay. Oops. Here we go. Okay, nice clean title bar up there. Great. Chapter 4, gas. I hear this is a very important concept. Great. Now we know how to update key portions of the DApp while preventing other users from messing with our contracts. Let's look at another way Solidity is quite different from other programming languages. Gas, the fuel Ethereum dApps run on. In Solidity, your users have to pay every time they execute a function on your dApp using a currency called gas. Users buy gas with Ether, the currency on Ethereum. So your users have to spend ETH in order to execute functions on your dApp. How much gas is required to execute a function depends on how complex that function's logic is. Each individual operation has a gas cost based roughly on how much computing resources will be required to perform that operation, e.g., writing to storage is much more expensive than adding two integers. The total gas cost of your function is the sum of the gas costs of all its individual operations. Wow. Because running functions costs real money for your users, code optimization is much more important in Ethereum than in other programming languages. If your code is sloppy, your users are going to have to pay a premium to execute your functions, and this could add up to millions of dollars in unnecessary fees across thousands of users. Why is gas necessary? Ethereum is like a big, slow, but extremely secure computer. Excuse me. When you execute a function, every single node on the network needs to run that same function to verify its output. Thousands of nodes verifying every function execution is what makes Ethereum decentralized, and its data immutable and censorship resistant. The creators of Ethereum wanted to make sure someone couldn't clog up the network with an infinite loop or hog all the network resources with really intensive computations, so they made it so transactions aren't free and users have to pay for computation time as well as storage. Note, this isn't necessarily true for other blockchain like the ones the Crypto Zombies author are building at Loom Network. It probably won't ever make sense to run a game like World of Warcraft directly on the Ethereum mainnet. The gas cost would be prohibitively expensive, but it could run on a blockchain with a different consensus algorithm. We'll talk more about what types of dApps you'd want to deploy on Loom versus Ethereum mainnet in a future lesson. Okay. In lesson 1, we mentioned that there are other types, uint, uint 8, 16, 32, etc. Normally, there's no benefit to using these subtypes because Solidity reserves 256 bits of storage regardless of the uint size. For example, a uint 8 instead of a uint, which is a 256, won't save you any gas. But there is an exception to this inside structs. Struct packing to save gas. If you have multiple uints inside of a struct, using a smaller uint is possible. Will allow Solidity to pack these variables together to take up less storage. Oh my god, this is exactly C. This is exactly C programming. Wow. This is so cool. Oh my god. This is great. That is great. I like that. All right. Anyway, so they make a struct. They make a mini-me struct where they specify the sizes, and mini will cost less gas than normal because of struct packing. Struct packing. Okay. For this reason, inside a struct, you want to use the smallest integer subtypes you can get away with. You also want to cluster identical data types together, i.e. put them next to each other in the struct so that Solidity can minimize the required storage space. For example, a struct with fields, UN32, UN32B, will cost less gas than a struct with cluster identical data types together. Okay. Yeah. Then UN regular and then UN32 because the 32 UNs are clustered together. Put it to the test. In this lesson, we're going to add 2 new features to our zombies, level and ready time. The latter will be used to implement a cooldown timer to limit how often a zombie can feed. So let's jump back to zombiefactory.sol. We'll add 2 more properties to our zombie struct, level 32 and ready time also 32. We want to pack these data types together, so let's put them at the end of the struct. Okay. So we're going to modify our zombie struct, add new data here. And they're going to be a uint 32 level and a uint 32 ready time. Cool, I think that's it. Awesome. All right, chapter 5. The level property is still streaming. No one's on. Almost at a half an hour. Should I send the link out again? Wouldn't hurt. I'm live. All right, let's go back to the monitor. 28 minutes. Okay, anyway. The level property is pretty self-explanatory. Later, we create a battle system. Zombies who win more battles will level up over time and get access to more abilities. The ready time property requires a bit more explanation. The goal is to add a cooldown period, an amount of time a zombie has to wait after feeding or attacking before it's allowed to feed or attack again. Without this, the zombie could attack and multiply 100 times per day, which would make the game way too easy. In order to keep track of how much time a zombie has to wait until it can attack again, we can use Solidity's time units. Solidity provides some native units for dealing with time. The variable now will return the current Unix timestamp of the latest block, the number of seconds that have passed since. Okay, yeah, Unix time. Traditionally stored in 32-bit number, this will lead to the year 2038 problem where 32-bit. Yes, the new Y2K. Anyway, 32-bit Unix timestamps will overflow and break a lot of legacy systems. So if you want our dApps to keep running 20 years from now, we could use a 64-bit number, but our users would have to spend more gas to use our dApp. In the meantime, design decisions. Great excuse. Solidity also contains the time unit seconds, minutes, hours, days, weeks, and years. These convert a uint of the number of seconds that in that length of time. So 1 minute is 60, 1 hour is 360, 3,600, 1 day, etc. Here's an example of how these time units can be useful. Time last updated now will return true if 5 minutes have passed. All right, so we're making a function, update time step. It's called now. Will return true if 5 minutes have passed, since update timestamp was called. False if 5 minutes have not passed. 5 minutes have passed. Public returns view. Last updated. But it doesn't show I was calling them, so whatever. We can use these time units for our zombie cooldown feature. Okay. Put it to the test. Let's add a cooldown time to our DAP to make it so zombies have to wait 1 day after attacking or feeding to attack again. Okay. Define cooldown time here. Uint cooldown time and set it equal to 1 days. Forgive the poor grammar. If you set it to 1 day, it won't compile. Since we added a level and ready time to our zombie struct in the previous chapter, we need to update create zombies. Okay? To use the correct number of arguments when we create a new zombie struct. Update zombies.push to add 2 more arguments. 1 for level. One for level and uint32 now cooldown for ready time. Okay, let's go back and read that again. Update the following line. To add 2 more arguments. Zombie. Name DNA. Why am I so confused? Okay. Let's look at this again. And update the zombies.line push. Since we added level, we need to update create zombies to use the correct number of arguments when we create a zombie struct. Update the zombies.line. Why am I so confused right now? Is it in zombie? But we have to update zombie up here, don't we? It doesn't say. Oh no, this is event. What am I talking about? Okay. Okay. Got it. Anyway. Okay, so it's right here. I messed up how to understand contrast. So essentially my mistake here was I was reading event as the constructor specifying the inputs, but really it is in this struct zombie, named zombie, that we're updating. No, wait. Right? Oh. Is that what's going on here? Zombie. So we'll do, first we'll type in what they want us to type in. 1 for level. And uint32 now plus cooldown time for ready time. And so in this contract, we have zombie. And I guess it is that you can initialize it like a, where did we write that? We can initialize the struct like a class. Cool. I don't think that really sat with me before. Okay. Anyway, cooldown time will equal the current Unix timestamp plus the number of seconds in 1 day, which will equal the Unix timestamp. 1 day from now, Later, we can compare to see if this zombie's ready time is greater than now to see if enough time has passed. To use the zombie again, we'll implement the functionality to limit actions based on ready time in the next chapter. Now that we have a ready time property on our zombie struct, let's jump to zombie feeding.sol and implement a cooldown timer. We're going to modify our feed and multiply such that feeding triggers a zombie's cooldown function, and zombies can't feed on kitties until their cooldown period has passed. This will make it so the zombies can't just feed on unlimited kitties and multiply all day. In the future, when we add battle functionality, we'll make it so attacking other zombies also relies on the cooldown. John Shea is now following me on Twitch. Are you in the chat or are you just following? Anyway, John Shea, if you're watching, thank you for tuning in. So where were we? I was checking a text. Sorry, I got caught up. Forgot I was streaming. But hey, we got a purple heart in the chat. All right. Thank you for the purple heart. And thank you for subscribing or following or whatever it is. Let's see. Anyway, this will make it so zombies can't feed on unlimited kitties and multiply all day. In the future, when we add battle functionality, we'll make it so attacking other zombies also relies on the cooldown. First, we're going to define some helper functions that let us set and check a zombie's ready time. Passing structs as arguments. You can pass a storage pointer to a struct as an... Oh, you can do pointers. Yes! This is C. This is just good C programming. I like it. You can pass a storage pointer to a struct as an argument to a private or internal function. This is useful, for example, for passing around our zombie structs between functions. The syntax looks like this. Function do stuff with zombies. It's an internal. You can pass a storage pointer to a struct storage there. This way we can pass a reference to our zombie into a function instead of passing in a zombie ID and looking it up, putting it to the test. Start by defining a trigger cooldown function. It will take, all right. Define trigger cooldown here. All right. Oop. Don't want to delete all the code. No, just this line. All right. Function private trigger cooldown. And it will take one argument, underscore zombie. Which is a zombie storage pointer. And this function shall be internal. All right, defining it'll take one argument. It should be internal. The function body should set zombie dot ready time equal to uint 32 now plus cooldown time. It will be an internal next create. All right, that's it. Next, create a function called is ready. This will also take a zombie. storage pointer argument named zombie. It will be an internal view function. Internal view. Because, all right. And returns bool. Right? Wow. Yeah, it's like good C programming. I really like this. The function body should return. Hey, John Shea, thank you for liking my tweet about me being live. That led you to be tuned in, at least for a little bit. I have 3 viewers? That's crazy. All right. Anyway, function is ready. The function body should return. Forgot how to do return, because this isn't, yeah, returns. Okay. Should return underscore zombie dot ready time. Arrow is less than now. So if it's less than now, is ready. Okay. Which will evaluate to either true or false. This function tells us if enough time has passed since the last time the zombie fed. Let's check our answer. Oh, no, let's not check our answer. Let's put in a semicolon first and see what our errors are. They did not like this one or that one. They didn't like that I have a returns here. Okay, so what did we do wrong? Storage zombie. It's an internal function. All right, show me the answer. Let's go. Let's see what's going on here. A space? That's what they're upset about? I can't have a space? Okay. Hey, if that's the complaint. Okay, they just wanted to have return. Right? Is it really just the space? Anyway, let's try again. Wow. Okay. So my real mistake was I did return for singular, or returns is plural, but up here it's returns. So okay, a little subtlety, but whatever. And let's keep going. We're streaming for about 43 minutes now. Anyway, chapter 7, public functions and security. This is a great language. This is a fantastic language. Now let's modify feed and multiply to take our cooldown timer into account. Looking back at this function, you can see we made it public in the previous lesson. An important security practice is to examine all your public and external functions and try to think of ways users might abuse them. Remember, unless these functions have a modifier like owner only, any user can call them and pass them any data they want to. Re-examining this particular function, the user could call the function directly and pass in any target DNA or species they want to. This doesn't seem very game-like. We want them to follow our rules. On closer inspection, the function only needs to be called by feed on kitty. So the easiest way to prevent these exploits is to make it internal. So let's go to our feed and multiply function and look at the code. Make this function internal, right? Because we only want what's there. We only want us, right? The owner. So let's make this internal. And let's make feed and multiply take our cooldown time into effect. Okay. First, okay, add a check for is ready here. Let's make feed and multiply take our cooldown time into account. First, after we look up my zombie, okay, we look up my zombie, right? We require that this person who's calling this function, zombie to owner, okay, and we look up their zombie ID, and let's see, let's add a require statement that checks is ready and passes my zombie to it. At the end of the function, let's call trigger cooldown time my zombie so that that feeding triggers the zombie's cooldown time. And a check for is ready here. Is ready. And it takes a zombie. So I believe we can just do my, or no, we don't have an underscore in here. My zombie, right? It's a storage type. Is ready, takes a pointer to a storage type. Beautiful. At the end of the function call, so once you create it, you call trigger cooldown on my zombie. So that feeding triggers the zombie's cooldown time. Oh, what did we mess up? Is ready, my zombie. Isn't that what they said? And passes the my zombie to it. Oh, require statement. Ah. Cool. Chapter 8, halfway there. Great. Our zombie now has a functional cooldown timer. Next, we're going to add some additional helper methods. We've created a new file for you called zombiehelper.sol, which imports zombiefeeding.sol. This will help to keep our, all right, we're going to add some additional helper methods. We've created a new file for you called zombiehelper.sol, which imports zombiefeeding.sol. This will help keep our code organized. Let's make it so zombies gain special abilities after reaching a certain level. But in order to do that, first we'll need to learn a little bit more about function modifiers. Function modifiers with arguments. Previously, we looked at the simple example of only owner. Modifiers with arguments. I like this. But function modifiers can also take arguments. For example, we make a mapping that maps to store a user's age. Okay. Modifier that requires this user be older than a certain age. Modifier, older than. It takes an age and a user ID, and it sees if the age of the user ID is greater than age. Okay. User must be older than 16 to drive a car in the US at least. We call the older than modifier with arguments like so. So it's a function drive car. It takes a user ID, and we wrap that in older than. You can see that the older than modifier takes arguments just like a function does, and that the drive car function passes its arguments to the modifier. Let's try making our own modifier that uses the zombie level property to just restrict access to special abilities. Put it to the test. All right, we're going to make in Zombie Helper, create a modifier called above level. So modifier above level. We'll take 2 arguments, level and and zombie ID. All right, so int level, int zombie ID, and we're going to require that zombies of zombie ID level is greater than or equal to the level Remember that we have to have the last line of the modifier call the rest of the function with underscore semicolon. What's wrong? The plus sign is wrong? Yeah, you're right. It is wrong. Typo. You've triumphed. Okay. Chapter 9. We're at 52 minutes, almost at the 1 hour mark. I might take a short break and make a coffee. Anyway, chapter 9. Zombie modifiers. Now let's use our above level modifier to create some functions. Our game will have some incentives for people to level up their zombies. For zombies level 2 and higher, users will be able to change their name. For zombies level 20 and higher, users will be able to give them custom DNA. We'll implement these functions below. Here's the example from the previous lesson for reference. Mapping. uint to uint, mapping store a user's age. We'll implement these functions below. Okay. Require that the user is older than a certain age. Function must be older than 16 to drive a car. All right, put it to the test. Create a function called change name. Change name. Oh, there's some people outside. We'll take 2 arguments, uint zombie ID. And new name string new name I'm not sure what that means. External. It should have the above level modifier. And it should take 2 arguments in the above level modifier, which are I see. 2 and zombie ID. I guess, yeah, it has to use the variables that are being passed there. Okay, and let's see, it should pass into blah, blah, blah. Note, call data is somehow similar to memory, but it's only available for external functions. So string call data Or is it on the outside? I forget. String memory, or it doesn't highlight it. Okay. In this function, we'll need to verify. So that means require that message.sender is equal to zombie to owner of zombie ID. Then the function should set zombies of zombie ID dot name equal to underscore new name. Create another function called change data below change name. Its definition and contents will be almost identical to change name, except its argument will be new DNA, and it should be past level 20. And of course, it should set the DNA to new DNA instead of setting the zombie's name. All right, cool. Let's do it. Copy. Pasta. Change this to 20. Change the name to change DNA, right? And we'll have to change this to it just wants a uint, right? New DNA. And we'll change this to DNA. And we will change this to DNA. Okay. These are external functions. Because you're checking that someone else, if it's theirs, they can modify it. Okay. Chapter 10, saving gas with view functions. Oh, we're almost at the end. All right, let's power through this. We're not even at an hour yet, 2 minutes away. Chapter 10, saving gas with view functions. Awesome. Now we have some special abilities for higher level zombies to give our owners an incentive to level them up. We can add more of these later if we want to. Let's add one more function. Our DApp needs a method to view a user's entire zombie army. Let's call it get zombies by owner. Deal. Function get zombies by owner. Anyway, this function will only need to read data from the blockchain, so we can make it a view function. Which brings us to an important topic when talking about gas optimization. View functions don't cost gas. View functions don't cost any gas when they're called externally by a user. This is because view functions don't actually change anything on the blockchain. They only read the data. So marking a function with view tells Web3 that it only needs to query your local Ethereum node to run the function. It doesn't actually have to create a transaction on the blockchain, which would need to be run on every single node and cost gas. We'll cover setting up Web3 with your own node later, but for now the big takeaway is that you can optimize your dApp's gas usage for your users by using read-only external view functions whenever possible. If a view function is called internally from another function in the same contract that is not a view function, if a view function is called from another function that isn't a view, this is because the other function creates a transaction on Ethereum and will still need to be verified from every node. So view functions are only free when they're called externally. Put it to the test. We're going to implement a function that will return an user's entire zombie army. We can later call this function from web3.js if we wanted to display a user profile page with their entire army. This function's logic is a bit complicated, so it will take a few chapters to implement. Create a new function called getZombiesByOwner. It will take one argument and an address named owner. Let's make it an external view function so that we can call it without needing any gas. The function should returns a uint int array as a memory data location. So we need to say I forget how you do this. Do we have it anywhere here? Returns address. Well, using my intuition. Why would we mess up? Okay. Why the type would go after, I don't know. Also wrong. Maybe they don't like the space there. What's going on here? Let's check it out. Okay, zombies external view returns uint memory. I had that, didn't I? My space is off. Is that it? Oh, I see. We're making the variable memory that is of type uint. Oh, I also forgot my open brace here. Maybe that was the problem. What is going on here? Oh, I never put them to begin with. Okay. All right, there we go. Cool. All right, chapter 11. Storage is expensive. One of the more expensive operations in Solidity is using storage, particularly writes. This is because every time you write or change a piece of data, it's written permanently to the blockchain. Forever, thousands of nodes across the world need to store that data on their hard drives, and this amount of data keeps growing over time as the blockchain grows, so there's a cost to doing that. In order to keep costs down, you want to avoid writing data to storage, except when absolutely necessary. Sometimes this involves seemingly inefficient programming logic, like rebuilding an array in memory every time a function is called and simply saving that array in a variable for quick lookups. In order to keep costs down, you want to avoid writing data to storage except when absolutely necessary. Sometimes this involves seemingly inefficient logic, like rebuilding an array in memory every time a function is called instead of saving that array. Okay. In most programming languages, looping over large data sets is expensive, but in Solidity, this is way cheaper than using storage. If it's an external view function, since view functions don't cost users any gas, and gas cost your users real money. We'll go over for loops in the next chapter, but first let's go over how to declare arrays in memory. Fixed length arrays. Interesting. Anyway, declaring arrays in memory. You can use the memory keyword with arrays to create a new array inside a function without needing to write anything to storage. The array will only exist until the end of the function call, and this is a lot cheaper gas-wise than updating an array in storage. Free if it's a view function called externally. Here's how to declare an array in memory. Get array external pure function returns uint memory. Uint memory. Oh, the type is uint memory, not variable name memory. Okay. Instantiate a new array in memory with a length of 3. You create a new uint array 3 called values, put some values in it. This is a trivial example just to show you the syntax, but in the next chapter, we'll look at combining this with for loops for real use cases. Note, memory arrays must be created with a length argument. In this example 3, they currently cannot be resized like storage arrays with array.push, although this may be changed in a future version of Solidity. If our getZombiesByOwner function, in our getZombiesByOwner function, start here, we want to return a uint array with all the zombies a particular user owns. Declare a uint array of memory type called result. Okay. Result, where is it? Set it equal to a new uint array of length. The array should be however many zombies this owner has, which we can look up from our mapping with the owner zombie count. There we go. Owner do we have that? Is that up here somewhere? Go to zombie feeding. This is zombie factory. Mapping. Owner zombie count. Owner. Okay. At the end of the function, return result. Okay. It's just an empty array now, but in the next chapter, we'll fill it in. What do we mess up? So let's just put this all on one line. Chapter 12. Oh, wow. We are almost there. For loops. We just hit 1:08. Can I stretch? Let's keep going. Chapter 12, for loops. In the previous chapter, we mentioned that sometimes you want to use a for loop to build the contents of an array in a function rather than simply saving that array to storage. Let's look at why. For our getZombiesByOwner function, a naive implementation would be to store a mapping of owners to zombie armies in the zombie factory contract. All right, hold on. For our getZombiesByOwner function, a naive implementation would store a mapping of owners to zombie armies. Yeah, you just like build it up here. Ah, I see. An address, and then you have it there. Right, you build the mapping. Like, okay. Then every time we create a new zombie, we would simply use zombie owner to zombies.owner.push to add that owner to that owner zombie array. And getZombiesByOwner would be very straightforward. You just call owner to zombies with the mapping you made. Okay. The problem with this approach is tempting for its simplicity, but let's look at what happens if we later add a function to transfer a zombie from one to another, which we'll definitely want to add in a later lesson. That transfer function would need to push the zombie to the new owner's owner to zombies array, remove the zombie from the old owner's owner to zombies array, push the zombie to the new owner, remove it from the old owner, and shift every zombie in the array to fill up that hole, and then reduce the length of the array by 1. Very, very, very explicit memory management. Step 3 would be extremely expensive gas-wise, since we'd have to write for every zombie whose position we shifted. And if we have 20 zombies and trades away the first one, we'd have to do 19 writes. Worst case, right? in order to maintain the array. Since writing to storage is one of the most expensive operations in Solidity, every call to this transfer function would be extremely expensive gas-wise, and worse, it would cost a different amount of gas each time it's called, depending on how many zombies the user has in their army and the index of the zombies, so the user wouldn't know how much gas to send. All depending on how many zombies the user has in their army and the index, yeah. Of course, we could just move the last zombie in the array, fill in the slot, but then we would change the ordering of our zombie army every time we made a trade. Since view functions don't cost gas when called externally, we can simply use a for loop in getZombiesByOwner to iterate the entire zombies array and build an array of the zombies that belong to this specific owner. Since view functions, so we can use a for loop, so we have our array of users. Okay, and iterate the entire zombies array and build an array of the zombies that belong to this specific owner. Then our transfer function will be much cheaper since we don't have to reorder any arrays in storage. And somewhat counterintuitively, this approach is cheaper overall. Okay. Using for loops. The syntax of for loops in Solidity is similar to JavaScript. Let's look at an example where we want to make an array of even numbers. It's a pure function, returns memory, unit memory, evens. 5, keep track of the index in the new array. Iterate through 1 through 10 with a for loop. If I is even, evens of counter. Gets I, increment this, counter plus plus, return evens. This function will return an array with the contents 2, 4, 6, 8, 10. Put it to the test. Let's finish our getZombiesByOwner function by writing a for loop that iterates through all the zombies in our DAP, compares their owner to see if we have a match, and pushes them to our result array before returning it. Okay, start here. Declare a uint called counter. Well, let me guess, we're going to set it to 0. Declare a for loop that starts from uint. All right. So we make a counter, we do a for loop. Uint I equals 0. Goes up I through zombies length I plus plus. This will compare the two addresses and see if we have a match. And inside the if statement, make an if statement that checks if zombie to owner of I is equal to owner. Add the zombies ID even. Where is evens? We made an evens. All right, so result array of add the zombies ID to our result array by setting result of counter equal to I. Oh, I see. Counter plus plus. That's it. The function now will return all the zombies owned by owner without spending any gas. Wowie. Okay, congratulations. I'm coming in at a minute 15 or so. Congratulations. That concludes lesson 3. Let's recap. We've added a way to update our CryptoKitties contract. We learned to protect core functions with only owner. We've learned about gas and gas optimization. We've added levels and cooldowns to our zombies. We now have a function to update a zombie's name in DNA once the zombie gets above a certain level. And finally, we now have a function to return a user's zombie army. Claim as a reward for completing level 3, both of your zombies have leveled up. And now that no name, the kitty zombie you want to blah blah is upgraded level 2, you can change name. Go ahead, give no name a name, then proceed to the next chapter. Okay? Give no name a new name. Your new name is going to be I'm looking around for something to use. Let's see. I'll name you Cap. Save. All right, it's now Cap. Let's advance to the next lesson. Congratulations, you've completed lesson 3. Right, we have our 2 zombies now. Show off your zombies, blah, blah, blah. Proceed to the next lesson. Awesome. So we'll get to the battle system. And, maybe I'll take a short break and come back and record that. But thank you for tuning in. Big thank you to John Shea for the follow and the comment. Don't forget to like and subscribe. And please reach out to me if you have any questions, comments, concerns. And yeah.